Now, magnet, by dictionary terms, is a piece of iron, or an ore, or an alloy, or other materials that has its component atoms ordered that the material has properties of magnetism, such as attracting other iron containing objects or aligning itself in an external magnetic field. Magnet was first found by about roughly 4,000 years ago, with a Greek shepherd named Magnus is said to have been tending his sheep in a region of northern Greece called Magnesia. He took a step and suddenly found that the tip of the nails that held his shoe together and the middle tip of his staff were stuck fast to the rock he was standing on. But so how does it work? So magnetism happens when tiny particles called electrons behave in a certain way. Now, all the objects in the universe are made up of units called atoms, and atoms in turn are made of particles called electrons. And other particles, such as neutrons, are protons. Now, the electrons spin around the atom's nucleus, and the spinning electrons form tiny magnetic forces. Sometimes many of the electrons in an object spin in the same direction, and in these cases, all the tiny magnetic forces form the electrons add up to make the object one big magnet. Now, electricity can also create magnets. Electricity is a flow of electrons, and as electrons move through a piece of wire, they have the same effect as electrons spinning around the nucleus of atom. This is called the electromagnet. Now, magnet has two ends called poles, and one of which is called the North Pole or North Seeking Pole, while the other is called the South Pole or South Seeking Pole. The force can either be attractive or repulsive. Now, if the North Pole is brought near the North Pole of the second magnet, the force is repulsive. Now, similarly, if south poles are brought close together, the force is also repulsive. But when the north pole of one magnet is brought near the south pole of another magnet, the force is attractive. Now, one important difference between electric charge and the magnetic poles are that positive or negative electric charge can easily be isolated. But an isolated single magnetic pole has never been observed. And if a bar magnet is cut in half, you do not obtain isolated north and south poles. Instead, two magnets are produced, each with north and south poles. Now, if the cutting operation is repeated, more magnets are produced, each with a north and a south pole. Now, the physicists have searched for isolated single magnetic poles which are called the monopoles. But no magnetic monopole has ever been observed. Now, there's this term called ferromagnetic, which are other materials besides iron that show strong magnetic effects. There is such as cobalt, nickel, gadolinium, and some of their oxides and alloys, and those are called ferromagnetics. Now, magnetic field is an invisible area of magnetism all around the magnet, and that is called magnetic field. Now let us suppose that we put the bar magnet or the horseshoe magnet onto the table and place the iron nail nearby. If we push the magnet slowly toward the nail, now there will come a point where the nail jumps across and sticks to the magnet. Now that's when we mean by magnets having an invisible magnetic field that extends all around them. Surprisingly, Earth is also one of the giant magnets that holds its magnetic properties due to its molten iron outer core, which is rich in magnetic materials. Now just like the bar magnet, Earth's magnetic field stretches out into space in a region called the magnetosphere, which can affect things around it. Now, when the energetic particles zooming in from the sun interact with Earth's magnetic field, we get this amazing auroras in the sky. Now, the other planets also have magnetic fields. Planets such as Saturn or Jupiter has fields stronger than Earth, while Mars and Mercury have weaker fields. Now, in the diagram here, there are geographic poles, north and south, and they are the axis of rotation, and they are also called the true north or true south. And the angle between true north and the direction a compass needle points is called the magnetic declination, which is the angle between magnetic north and true north. The compass needle points to our location called the magnetic north, which is the point on the surface of the Earth where the magnetic field points directly towards the Earth's center. And the angle that the Earth's magnetic field makes with the horizontal at any point is referred to as the angle of dip. Now him, which the Hans Christian Ørsted, was a Danish scientist who explored the relationship between the electric current and magnetism. As I say, current is the flow of electrons. Currents create their own magnetic fields in closed loops, which magnets are known to induce or create current in wires. Ørsted experimented with this using a compass, which uses the magnetic poles of the Earth to show which direction you're facing. By bringing the compass near a closed current loop, he was able to interfere with the magnetic field and cause the compass needle to move. Now to show the process, a thick insulator copper wire is taken and connected with a battery in a way that current flows, which is from south to north direction in the wire. Now the compass needle is placed under the wire. Now when the electric current is passed through the wire from south to north directions and the wire is placed over the compass needle gets deflected towards the west direction. And when we reverse the direction of current in the wire, the compass needle gets deflected in the opposite direction, which is east. And when current is switched off, then there is no deflection in the compass needle. Now the conclusion is that the deflection of compass needle, which is that whenever there is current in the wire, it produces a magnetic field around it. It also shows that the moving electrons can create a magnetic field. The magnetic field created by the current goes in circles around the wire, like this. Now the last concept to be explained is the right-hand rule. Now right-hand rule is used to find the direction of the magnetic force, and it states that if we put the thumb of our right hand in the direction of the current, the magnetic field will wrap around the wire the same way your fingers will. So to show the process, we grasp the wire with our right hand so that the thumb points in the direction of the conventional or the electrical current. Then our fingers will encircle the wire in the direction of the magnetic field. Now, the magnetic field lines due to a circular loop of current-carrying wire can also be determined in a similar way by placing a compass at various locations near the loop. Yet, the magnetic fields are not uniform like this figure. The fields are different in magnitude and direction at different locations.